Hello, and welcome to Astronomy 100. In this video, what we're going to discuss is the aftermath of the death of a very, very massive star. If you remember from the previous video that the highest mass stars in our universe will die by literally exploding. What happens is the core of the star collapses, the energy from that collapse and the fusion process that ensues has to escape very quickly. The star is not able to let it escape fast enough, and so that massive amount of energy rips through the star to the surface and explodes the star into space. And we call that a supernova. And what we're going to do in this video is talk about the aftermath. In other words, what happens when this occurs, and we're going to also include various examples of where we've seen this occur in places around our universe. So let's go ahead and get started. The supernova itself, it's important for you to remember that the supernova is the event. So a supernova is a verb, it's not a noun. It's not an object. There is no such thing as a basket full of supernovas. It is an event. So the supernova is the explosive death of the star itself. And when the star explodes, the amount of energy that is released is enormous. It's very difficult to get people to understand just how much energy we're talking about, but I'll do my best. When a star explodes, it is one of the most energetic things that the universe is capable of producing. In other words, it's one of the biggest explosions that is possible in our universe. The energy that is released in a supernova is enough to rival the total amount of energy that this star has produced in its normal phase of its existence for its entire life. So imagine taking a star and having its energy that it produces over its normal lifespan all bottled up, and then in one single moment release that energy out into space. So you can get the equivalent of millions of years worth of energy released in just 1 or 2 or 3 or 4 seconds. So it's an incredibly energetic thing. And it is something that becomes quite visible at tremendous distances because of the energy that is released. Now, this process of stellar death by supernova is something that is relatively rare. In any given galaxy, it happens about once every 75 to 100 years. So in a galaxy that is very typical, similar to the Milky Way, what will happen is about once a century, a massive star will die by exploding. And we'll see some examples of this here in just a minute. Now, the odd thing is that the Milky Way is long overdue. Even though on average, statistically speaking, the Milky Way should have had a star die by exploding by a supernova about once a century, we have not had one happen in our galaxy for 400 years. And as of the taping of this video, again, we are long overdue by about 400 years since the last one. Now, the event of a supernova is something that occurs in other galaxies. And let me show you an example of one that occurred back in 1987 that is the closest supernova to us that has occurred in at least modern history. And it occurred in a galaxy that is a neighbor to the Milky Way. The Milky Way galaxy is not alone in our universe. There are many, many other galaxies, and we'll talk in a future video about that. But the Milky Way has 2 small galaxies that are companions to the Milky Way. And these 2 small galaxies are not visible from the northern hemisphere. You have to be in the southern hemisphere to see them. And the first European explorer to see these galaxies and then come home to tell everybody else about them was Magellan. So these galaxies are called the Clouds of Magellan, or Magellanic Cloud, and there's 2 of them. One is big and one is small. The one that is the bigger of the 2 is called the Large Magellanic Cloud, and this distance from where we are, the sun's location in the Milky Way is right about here, and so the distance from the sun's location to where this star blew up is a distance that's about 170,000 light years, which is a tremendous distance. So 170,000 light years away from us, a star blew itself up that we witnessed in 1987. Now let me show you the before and after. So here is the before picture. And although this seems to suggest that there was a very large arrow in the sky that night, it's not quite the way it looks. What happens is when a star blows up, these things tend to catch us by surprise. And so what happens is we tend to look through our archives of pictures to try to find the star that was the one that blew up. So this is an archival picture, and the arrow indicates the star that was the one that ended up blowing itself up. So this is the before picture, like a before and after picture. Now you'll notice it's bright. It's not maybe the brightest star in the entire sky. It is bright, but there are stars that are very similar in brightness. So this is the way the star normally looks. But in early February of 1987, overnight, it went from this to this. And what you'll notice is the brightness change is tremendous. It's an incredible release of energy when this star blew itself up. So the energy release is enormous. And of course, even at a distance of 170,000 light years, this thing became very noticeably brighter, and it obviously caught the attention of the astronomers that were working at observatories in the southern hemisphere. When a star blows itself up like this, we want to study it. And one of the most important things to study is how its brightness changes over time. So what this is called a light curve. And a light curve is one that shows you the brightness of an object over a period of time. So you'll notice the bottom says days, and then the vertical axis has magnitude. This is actually absolute magnitude. So what you'll notice is the numbers are becoming bigger in a negative way, more negative to the top, less negative to the bottom. If you remember from a previous video, the magnitude system is sort of backwards. The more negative the number is, the more energy the object is actually producing. So notice as the days went by, when we look at an object that blows itself up, you'll notice that it gets brighter over time, reaches a maximum brightness, and then as the weeks and sometimes months go by, it fades from view. So when an object like a star blows itself up, it becomes very, very bright, and then it fades from view over a period of maybe 2 or 3 months until it becomes something much fainter than it previously was. So these become very, very bright, and then they become fainter over time. Now, as I said, the Milky Way galaxy is long overdue. So since the invention of photography, we haven't seen anything in our galaxy blow up. No stars have blown up for us to observe. But what we can do is we can observe this happening to stars in other galaxies. And so let me show you a series of before and after pictures. So this is a normal galaxy, lots and lots and lots of stars. But overnight, one of the stars in this galaxy blew up. And notice how it's a little bit maybe underwhelming when you think about, wow, that's very bright and here's what we're talking about. But think about it, how, let's go back to the before picture. Think about how these are all stars that you can't even see as individual dots because they're just too faint and there are too many of them too far away. But suddenly, one of them becomes distinctly brighter. So this is a single star that blew itself up, but it is outshining all of these other stars. In other words, it is the equivalent of the energy of many, many millions of stars all put together. So one star blows itself up, and even at many millions of light years distance, we can actually see this happening. Let me show you a few more examples. So here's another before and after. So a star that's right here blew itself up, and notice how it becomes quite obvious when it looks like a star comes from nowhere. It looks like there's nothing normally there, suddenly something becomes very bright. Here's another example here. There was a star near the very center of the galaxy we call the Whirlpool galaxy that one night blew up, and so we get this big spot of light where we previously didn't see one. Again, remember, lots and lots of stars are so faint we can't see them, but this one becomes bright enough that it's almost the same brightness as the core of this galaxy. Here, this one was incredibly bright. Look at how bright that is compared to this entire core of this galaxy. Enormous amount of energy being produced. And then one last example. So when a supernova occurs in a distant galaxy, we can see these, even though these galaxies might be millions of light years away. That's just that much energy being produced. Now, the last part of this I want to discuss is a concept that's very critical, and it has to do with what's left over. when the star blows itself up, the envelope of the star and part of the core has exploded out into space. And so the leftover from the explosion is called a supernova remnant. In the world of military bombs, the material that explodes outward is often called shrapnel. That's the stuff that blows outward and it destroys buildings or unfortunately hurts people. So this is sort of the shrapnel. This is the material of the star that is blown up and it is now blowing out into space. So each one of these pictures is a supernova remnant, and it's all of the material that used to be the envelope and again part of the core of a star that was somewhere right in here that blew itself up. Now this one is quite old. You can see the shape of it. It's clearly a cloud that's getting physically bigger and bigger and bigger. And we can run it backwards. We can basically say, if we know how big it's getting day after day, we can figure out how long ago this star blew up. And this one blew up anywhere from 12 to 14,000 years ago. And it has now expanded its material. This is essentially an explosion that is continually happening. It is just getting bigger and bigger as this material is expanding out into space. Here is another supernova remnant. This one's much older. Notice the material has had a chance to really drift out into space. These are more recently formed supernovas, remnants at least, so you'll notice that a star somewhere near the middle has exploded its material outward. Now this one here I want to show you, this one right here is actually part of this right here, so it's just a close-up. What I want you to notice is this edge right here. This is a shock wave. So all of this material is moving like this, and this is the shock wave of that material pushing through space. So the idea is that when a star blows itself up, all of its material gets pushed out into space, and we'll come back to that in just a minute. But it's important at this point to fill in our last line. If you remember, this is showing you the entire evolutionary sequences and stages of stars. We've previously talked about low mass stars, previously talked about intermediate mass stars. Now we can add high mass. The highest mass stars in the universe go through all of these stages of changes, but eventually die by becoming a supernova event, the explosive death of the star itself. But remember, they go through the same series of events, but the high mass stars do it faster than any other mass category. Now, one last little piece related to what we started to talk about is the material that gets blasted out into space is actually very important to you and I. Because if you think about it, all of these atoms, these heavy atoms that were produced in this star, are now being pushed out or exploded out into the interstellar medium. And the atoms that are being pushed out into the interstellar medium were created through the process of fusion at the core of this now dead star. So this is a supernova remnant called Cassiopeia A, and when we use special filters, we can actually figure out what type of atoms are the atoms that make up this cloud. In other words, what is the element of each of the atoms in this cloud? And here are three examples. When we use a very special filter that will show us only the light from the element silicon, what it shows us is that this cloud has silicon atoms. And silicon atoms are important because many, many rocks here on Earth have silicon atoms as part of those rocks. And of course, silicon is what we mine to make computer chips. Now, the calcium atoms are highlighted in this picture. So it's the same cloud, but it's showing you where calcium atoms are. And calcium is important. There's calcium that makes up your bones. There is iron in this cloud. Iron is critical because iron is in your blood. So if you think about it, the very atoms that make up you, the very atoms that make up all of the materials of any form of life on Earth, humans or otherwise, is actually manufactured inside of stars. Carl Sagan many years ago used to like to say that we are made of star stuff. And that's the point he was making, is stars of high mass create the elements that you and I are made out of, the Earth and everything else. And if these stars didn't live, die, and explode, those elements would not be available for us to live. So it's quite an interesting thing to see our connection to the lives and the deaths of very massive stars. Now, what we're going to wrap things up with in the next video, or 2 videos, is what happens to that core that has collapsed just before the star blew itself up. Some interesting things lie ahead for us, and we'll talk about those in the next video. I hope you'll join me.